Pues bienvenidos a todos. Gracias por asistir a esta sesión del Seminario de Ciencia de Datos de la División de Ciencias Básicas e Ingeniería de la UAM Iztapalapa. Vamos a dar inicio al, ¿cómo se dice?, al seminario con el invitado especial que nos encontramos hoy. Es el profesor Dr. Anderson Rocha, es director del Instituto de Computación de la Universidad de Campinas en Sao Paulo, Brasil. Nos va a hablar de inteligencia artificial. La plática va a ser en inglés. Los estudiantes o los colegas que quieran preguntar en inglés son bienvenidos también. Bueno, en portugués también, supongo. No hay problema. Podemos hacer de todas formas la traducción en el caso que alguien quiera preguntar en español y fuera algo más intrincado, que posiblemente el profesor nos pudiera platicar, ¿no? Pero de cualquier manera, les agradeceríamos quizás al final dejar todas las preguntas, sería lo más conveniente, a menos que requiriéramos tener algún tipo de precisión respecto a la plática. Pero bueno, entonces, sin más preámbulo, le cedo la palabra. I'm going to switch to English now. I'm going to let Professor Anderson Rocha to speak. So if someone has some question, please do it at the end of the talk, or using the chat. It would be a great idea as well. So please, Professor Anderson Rocha, welcome, and it's all yours, please.
Thank you very much, Hector. It's very nice to be here, and it's one of the positive aspects of the pandemic is like at least one positive aspect is that we can meet and do these nice discussions. Thank you once again for the invitation. I'm going to discuss with you here one aspect that I've been discussing with several groups worldwide in the past 2 years. It's about what's called Convergence Revolution. And I'm going to explain what it is and what we are doing here at the Artificial Intelligence Laboratory that's connected to this Convergence Revolution. And I'll give you some examples of that. And if you have questions, you can do them on the fly. It can be in Portuguese or Spanish or English. It doesn't matter. I didn't dare to present to you in Spanish because I'm still learning, but I can understand and read most of it. The subject of today, it's being propagated by several researchers, mainly by Ray Kurzweil from Google and Peter Diamandis from Abundance 360 and some other researchers, and I'm one of them. So to give you a little bit of perspective, I'm a professor at the Institute of Computing, University of Campinas. It's known as UNICamp. I've been a professor there for 12 plus years. I'm an expert in artificial intelligence and complex data. For about 20 years, I'm working with these subjects. And the research that I do in my lab is both theoretical and applied. So I coordinate a lab now. It's called Recod.ai. This lab has about 60 researchers, including master's students, PhD students, and postdocs. It's a very multi-ethnic and lingual group. I have PhD students from Italy, China, Iran, Bangladesh, Australia, Peru, Colombia, Ecuador, Brazil, of course. So it's a very, very dynamic group with multiple cultures. This is one of the most productive groups in artificial intelligence in a university in Latin America. So if you are interested in getting to know more about our program here, we are with the applications open for masters and PhD. So let me know later if you are interested. I don't know if you know, but UNICamp is a totally free university. And if you are accepted, you also have the opportunity to receive scholarships. As a little bit about myself, I'm a Microsoft, a Google, and Tanshituan faculty fellow. I'm listed currently among the top 1% scientists worldwide. So some of the research that I'm going to show you here has been recognized, and some of them are being applied in practice. So this is very good. every year before the pandemic, at least, I usually stayed as a professor in one university at least per year. And here are some of them, some of the last ones that I visited. So what we're going to talk today, I'm going to give you a little bit introduction of what's AI, because the whole definition of AI has changed. In the beginning, it was one thing, and as of 2017, 2018, the meaning changed. It's more updated now, so to say. I'm going to give you 3 examples of what we do in the lab in terms of metabolomics, neuroscience, and digital forensics. And then I'm going to end up with some questions about what are the challenges that we have normally in the field, at least in my lab, and where are we headed to, what we want to do in general. Okay. The talk is about 45 minutes, 50 minutes, and then we can have like a 20, 30 minutes discussion according to the time that Hector has available. So many of you probably have heard that we are living the 4th Industrial Revolution. We started around 1760 with the first Industrial Revolution with the steam machines. That was updated a few years later, around 1820, with the electricity. And we know that electricity changed the lives of pretty much everyone. And in the years 1900 and on, especially after the Second World War, we had the computing revolution. And more recently, we have the intelligence revolution, which is called the Industrial 4th Revolution. But if you consider the whole existence of humankind, this is the 50th great revolution that we have. The first one, of course, is the agricultural revolution, and then the 4 revolutions afterwards. Then we are living now the 5th revolution in history. And what revolution is this? This revolution is called Convergence Revolution. What is convergence? It's a point in which many other science and technology developments converge together to a single point. And right now we are facing this revolution mainly in 5 big areas: in biotechnology, genetics; in nanotechnology, robotics; Internet of Things; and AI, artificial intelligence. And I'm going to give you some examples of why we are saying this. Okay. So this is called, in short, GNR-IoTI. So the first one is biotech and genetics. And why are we living the revolution in biotech and genetics? Probably you have heard of the new vaccines for COVID-19. And what do some of these vaccines have so revolutionary? First of all, the first revolution, the first great paradigm change with these vaccines is that we were able to do one vaccine for a big threat in less than a year. So this is the first time in history that we do something like that. And especially with 2 of them, we did that with what we called messenger RNA, which is the cousin of the DNA. And this is the component of the cells that deliver messages. And by changing this guy, we are able to change something inside the cells so that we can tell the cells that when they see something weird, like components of the SARS-CoV-2, the virus of the COVID-19, they start producing antibodies. And this is present in the vaccines of Pfizer and Moderna. But also, we have a very nice example for the vaccines of AstraZeneca from England. AstraZeneca does not use mRNA, but they use modified DNA. So they get an adenovirus, which is a common flu virus. They change its DNA to have small sections of the SARS-CoV-2 COVID virus. And then they put that in the system, and the body starts producing antibodies. So this is the nice thing about what's happening. And in 2020, Two women received the Nobel Prize for Chemistry for discovering one technique about 8-9 years earlier called CRISPR-Cas9. So CRISPR is a technique known as the cell scissors. So it's a technique that allows you to go to the cells and cut DNA and shut some genes off, turn some genes on, or inserting some sequences, programming the cells to do something. And this is a revolutionary thing because it allows us to edit the code of life. It allows us to fix some diseases that are genetically transmitted. It allows us also to do bad things. And these are things that we really need to think about, like, for instance, editing the genome for someone to be more, to be stronger, to be taller, to be smarter. And we all know that whenever we try to do something, it's a bad thing, right? But we have the positive sides as well. So this is one area that's changing the way that we live. Another area that's changing the way that we live is nanotech. So we're starting to produce smaller and smaller and smaller devices that allows us to monitor many different things. We can monitor, for instance, the weather with better robotics, better nanotechnology that we can spell, that we can disperse on the air, and they will monitor the atmosphere for changes. We can also develop nanobots to go to the body and analyze components of the human body or any other animal body. And all of this is being done with the reduction of costs and the reduction of size of these components. Another area that's the fourth component of the convergence revolution is robotics. We all know that we are having a strong impact in terms of nanotech, but we are also having a strong impact in terms of the new kinds of robotics that we use. Years ago, the most common robot that we had was the robot for cleaning houses, like Roomba, that they used to around the apartment and soak in all of the dust, and then you could have a cleaner house. But now we have many other robots, like use it for rescue missions. They are used for environment analysis, for industrial plants, for creating other machines, to fabricate cars and other things. So robotics is the fourth component of this convergence revolution. And another component of this revolution, actually robotics is the third, and the Internet of Things is the fourth, and vice versa. Some people disagree on that, but if robotics is the third, Internet of Things is the fourth, which is allow the sensors to communicate among them, to communicate to each other. And so if you have all of this communicating, you produce a massive amount of data that, combined with artificial intelligence, they create this fifth revolution, the revolution of convergence. And at the center of everything here is artificial intelligence, because lots and lots of data are being created, and we need to make sense of this data. So this is the convergence revolution. But what is AI? So for many years, many people thought that AI would be the capability of a system to behave intelligently, to pursue some actions. But this is a recursive definition, and it's too open. So more recently, around 2018, a more well-defined form appeared, proposed by Kaplan and Hanley. And we use this definition today as our guide. So what is AI according to this guide? The ability of a system to correctly interpret data from the world, external data, learn from given problems, and use these learning capabilities to achieve specific objectives and tasks through flexible adaptation. What am I talking about here? I'm talking about that we need to have some mechanisms to observe the world, some sensors. We need to go to the world and capture data. So AI encompasses all of this. So we need sensors, go to the world, collect data. After we collect this data, we need to learn. We need to learn some patterns. We need to discover patterns. We need to learn some properties. We need to learn rules. So this is the learning capability. This is where, for instance, machine learning comes in. Once we learn, we need to make sense of what we learned. So we need to interpret the learning that we had. So this is the interpretation part, the representation of knowledge part. After we do that, we can take action. So to take action, I need to have actuators to change things in the world. This can be the physical world that we are living in, the 3D world that we are in, or it can be the virtual world. It can be an action online. Okay, but we need actuators to go to the world and change it. And we also need the capability of flexible adaptation. It means that we cannot just learn some things, stop in time and use that knowledge forever. No, we need to be able to adapt over time so that once new data comes in, we adapt on top of this new data and we flexibly adapt. Okay, we update. So this is the definition of AI that we use. And this is the definition that I'm gonna discuss with you in the problems that I'll give you as examples. And many people think that AI is something new, especially appeared around 1950 with the seminal paper by Alan Turing entitled Can Machines Think? But AI is much older than that. Actually, one curiosity here, AI is older than computer science. So people started discussing the possibility of a non-natural, an artificial being learning something before actually computer science concepts. So one of the first registers that we have about AI goes back to Greek mythology, in which one bronze automaton was created to protect of Crete in Greece. And according to the mythology, it was created by Hephaestus, the god of metallurgy, at the request of Zeus. So the journey to artificial intelligence starts with dreams, just like our journeys. People started to dreaming about an artificial being being able to learn automatically. And note that this was not the word robot, because the word didn't exist that time. It was automaton. But later on, also Aristotle discussed it in his masterpiece, Politics. He also discussed it there, the only condition that he could foresee in which we would not need masters and slaves, bosses and employees, coordinators and subordinates. The only situation it would be if we were able to create an artificial being capable of intelligent anticipation. Look, this was discussed in 350 before Christ. So AI has been around for many centuries. And then it kept developing, and in the Renaissance, we had the Night Automaton by Leonardo da Vinci. I had the opportunity to visit this one here in Milan, and it's very, very nice. It really looks like a robot, but of course it's not a robot. It's a model that Da Vinci created because he envisioned wars being waged only by automatons to save lives. Then also in the 16th century, we had the legend of the Golem, in which Rabbi Judah Loew from Prague, he decided to create a small doll made of clay to help him clean the house. So we can say that this is the first version of Roomba, created by Rabbi Judah Low in Prague. And then around 1920, we have the first version, the first time that the word robot was used. Actually, robot comes from the Czech. In Czech, robot means slave work. So this was a theater piece, so theater play that Karel Capek presented in Prague. And then in this piece, he had a lot of robots, or in other words, a lot of slaves factory. So this is when we had the first mention to this word robot, and then we have it until today. But then in the 50s, we had the birth of the modern artificial intelligence proposed by Alan Turing in his seminal paper. And just 6 years later, we had the AI founding event proposed by Marvin Minsky, Rochester, Claude Shannon, and John McCarthy, the famous Dartmouth AI workshop. And then we are today here discussing AI. But what does AI encompass nowadays? So we have what we call AI constellation nowadays to show that AI is much bigger than we think. So this is the map of AI. And I'm going to zoom in here, but this is like the zoom out just to show you that AI is connected to many different areas of knowledge today. And let's see some parts of this. So first of all, let's divide this in 4 quadrants, and let's go first to the quadrant on the top left. So the quadrant on the top left is where we have the whole area of machine learning. So here we have the problems in which we have examples to learn from. So this is supervised learning. Or we don't have examples at all, but we need to find patterns. This is unsupervised learning. Perhaps we don't even have that. Perhaps we only have a rule for what's correct and what's wrong, what is wished for, and what should be avoided. So, for instance, if I design a robot and this robot hits the wall, this is not something that I want, so I can penalize the robot. Or if I devise a smart car, an autonomous car, I would not like to hit someone. So this is a bad behavior and I should penalize it. So if I do that, I'm using what we call reinforcement learning. And this is one area of machine learning as well. So here are the 3 most important areas related to machine learning. But on the other side, on the quadrant on the top right, we have the whole area of how we interact with the world. It can be the things that we hear, that we see, that we touch, everything related to seeing, analyzing, collecting data from the world. This is the area of perception. It can be computer vision, if we are talking about lenses and images and videos. It can be tactile sensors, if it's something that I use to manipulate things in the world and have the sense back of what I'm manipulating. It can be artificial lenses. It can be sensors for sound, sensors for waves, for distances, everything. So this is what we call perception, which is connected to artificial intelligence. Because remember the definition of Hanley, AI is all about how I perceive the world, collect the data, learn on top of this data, interpret this data, and use this interpretation to take action on top of the world and adapt flexibly. So this is totally connected with the definition that we just saw. But it continues. On the quadrant on the left, but the bottom left, we have the whole area of how we connect the brain to the machines. It can be smart cochlear implants that allows people to hear better, or it can be enhancement for vision for people with damages. It can be some initial sensors that we connect to the heads to control some objects. So these are known as brain-computer interfaces, or BCIs. Okay. If, for instance, we have someone that loses the arm and needs a prosthetic, we can use this prosthetic with AI, and we can connect the wires to the nerves, so that when this person sends a message through the brain, from the brain through the nerves, these AI processors enhance that signal to send the signal to the prototype. So this implant can also send back information from the word to the brain. So this is being applied nowadays with very good success. People are recovering their capability of walking or manipulating objects with artificial arms and legs using BCIs. When we try to transform these algorithms from the representation from the virtual world to the physical world, we have what we call the embodied AI. So we need to transform, to put these algorithms in a robot, for instance. So this is embodied AI. Or we can put these algorithms in a car to have an autonomous car. This is embodied AI. A car, an autonomous car, is just a robot in wheels. So remember the movie Transformers? Autonomous cars is just like that. We are putting a computer in a car, and we are putting AI in this computer, so everything in the car is basically a robot. And on the bottom here, we have the whole area of data science, making sense and connections of patterns in the data. The past was known as business intelligence, but all of that has been incorporated into what we call nowadays data science. And this data science includes data mining, edge analytics, ontologies, knowledge representation, big data. Everything here is in the area of what we call data science. And the final big piece here is how we understand language. It can be speech, it can be written, it can be text. So all the area of natural language understanding. Okay, so all of these compose what we call AI constellation, and this is the most recent definition of AI, which is not recursive as the ones before. So now that I put you in context of what we are talking about, what is AI in the context that we are discussing here, let me give you 3 examples of what we are doing in our lab. Okay, so the first one is metabolomics. So to give you a sense of it, what is metabolomics? So we know that many biological systems, pretty much all of them, cells, tissues, organs, they produce, transform, and consume what we call the small molecules all the time. And normally these molecules, they are responsible for like defending the body against intruders. They are responsible for the growth of cells, and they are also responsible for stimuli. For instance, when you take a medicine and you need to make the medicine to work on the body, the ones responsible for taking that medicine to the bodies will be these small molecules. So the field of metabolomics is the one that seeks to uncover the functions and responses in organisms in all these in which a biological system produces, transform, and consume small molecules. And if you think of the DNA code, I think that in Spanish you call it ADN. If you think of the genome and all the information in the DNA, everything that's related to the DNA is one area called genomics. If you study the process of the transformation of DNA information to a messenger RNA to send some message to the cells to produce something, this is transcriptomics. So when the RNA arrives in the cell and translates that message, that information to the cell to produce some proteins, for instance, this is called proteomics. And when we have things that are related to the environment, to the phenotypical features, so the study of these phenotypical features that changes the body, this is metabolomics. So when it's related to the DNA is genomics. When it's related to the phenotypic factors or to the environment, this is metabolomics. So it captures phenotypical factors. These factors can be inside or outside. They can be endogenous or exogenous. If they're endogenous, we are talking about the production of vitamins, fatty acids, sugars. For us here, this is not of interest. We are more interested in what we call exogenous factors, when the body was affected for something coming from outside. Why? Because we are interested in detecting things that change the body somehow, like viruses. And the problem is the human body has around 20,000 metabolites, or these small molecules. And how can we identify which ones change when someone gets a virus, for instance? Without AI, that would be very, very difficult. So this is where AI comes in. And when we bring together AI and metabolomics, we open the whole area of possibilities, like discover new drugs, new nutrients, detect diseases, predict diseases, toxicology to identify like if someone consumed cocaine or something like that. And we in particular are interested in a few diseases. So here we are interested in the analysis of intra and interpatients. We want to find biomarkers, or in other words, which small molecules are related to a particular disease. And this is in collaboration with the pharmaceutical lab, a pharmaceutical school here at the University of Campinas. So we do the AI part and they do the biological part. We have done four investigations, four big investigations in this area until now. The first one is a new detector for Zika virus. This was around 2018. Then after that, we discovered some factors that are associated with obesity in persons that can develop diabetes. In 2020, we developed a detector for this disease. That's a fungal disease called paracoccidiodomicose, which, just for short, we call it paracoco. And of course, in the last 2 years, we are investigating detectors for COVID-19. So this is a collaboration of more than 4 years, and we have like publications, software, and also some patents on this topic already. And today I'm going to give you a walkthrough of what we did for COVID-19. So we developed a test, a new detector for COVID-19. It's patented and licensed for free for the Brazilian government. The idea here is, instead of using a swab that you can collect those weird and very bad exams that you do with PCR, that you need a swab into the nose. I did one of that and it's terrible. Our idea here is to collect blood from a person. Just blood, typical blood you do in a pharmacy. So we collect the blood, then we use the machine to separate the blood component plasma. So we work with the plasma, which is one component of the blood. That in color part of the blood is plasma. So this plasma goes to a device called the mass spectrometer. And this mass spectrometer creates as a vector of around 14 to 20 numbers, which are the atomic weight of those small molecules that I mentioned earlier. So now the question is, if I have these signatures for each person, which ones change in the presence of the virus, of the SARS-CoV-2 virus? So we use techniques of artificial intelligence and explainable artificial intelligence, what we call XAI, to identify what changed. And once we identify what changed, we are also interested in this deciding if that change is biologically plausible. That's why we have the humans in the loop that validate the markers. If they don't make sense, we discard them, let the algorithm know, and the algorithm refines itself and gives us another set of markers. So we keep doing this, and in the end, we are able to identify around 30 markers associated with the presence of the COVID-19 disease. So these components are, for instance, prostanoids, they are fatty acids, lysopcs, some biological components that change in the presence of the virus. And here is an example on the left, the separation of the two classes, normal patients versus the ones with COVID-19. And on the right, on this list of bars here, you can see the names of the components of the blood that we identify that augment, that increase their presence in the blood when the person has COVID-19, and the ones that decrease on the person when the person doesn't have COVID-19. So here is the result that we had, and this test is being validated now by the national labs and can be something to help to have something additional to test for COVID-19. This is basically AI and metabolomics. Another research that we investigated here is in neuroscience. In neuroscience, we are particularly interested in Alzheimer's. So with the advance in imaging capabilities, we have non-traditional data. The traditional data is like text, audio, images, and so on. But when you go for neuroscience, for instance, the data that you have is a 3D, is a 3D volume. It can be a mass magnetic resonance image, MRI, or computerized tomography, CT, or 3D, 4D ultrasound. These are different kinds of data, and we need to work with that. So in this project, we explore a possible way of detecting Alzheimer just based on the MRI. So our question here was, is it possible to detect Alzheimer's just based on the MRI? Because we know that we can combine later with previous information of the patient, family history, and other things. But we wanted to answer the question, what can we do if we use only the image? So again, we used inter and intra-patient analysis. This was in collaboration with neurologists and neuroscientists from the National Institutes of Health in the US, the University of Calgary in Canada, Unicamp, and the University of California, LA. And it's a collaboration of more than 4 years. We also produced data sets. We have some publications, and all the software is open source. People can use and improve upon what we did. So we know that Alzheimer's is a terrible disease. It affects around 37 million people worldwide. Only in Brazil is 1.3 million. And it's a difficult and multifaceted diagnosis. It's very difficult to detect Alzheimer's. It's sometimes the condition appears before the symptom. Early diagnosis is essential to improve quality of life. In Brazil, in particular, we have around 50,000 new cases per year. So it's definitely a must-study factor. So here are the differences. So if we receive an image, like a 3D volume of an MRI, We want to separate what is called cognitively normal, the person that doesn't have problems with Alzheimer or dementia. And also we want to separate that from Alzheimer's traces. So what happens when the person starts developing Alzheimer's? The volume of the brain starts shrinking, and some parts of the brain start shrinking earlier. So before the whole brain starts to shrink, some parts in particular start to change their shape. So this is what we need to detect. So we start with collecting a big data set of MRIs. So we created one of the largest MRIs data set available. We collected everything available for free in the internet from many different sources, and now something about 20,000 volumes, 20,000 3D MRIs of different patients. Of course, they come from different sensors, they come from different times, and then we need to put them in the same scale. So we need to register them. So to register them, we use the Atlas MNI 152 ICBM. This is like a standard for brains, and it's created by the Montreal Neurological Institute. So every 3D image is projected on this atlas to have the same size and orientation. Then after that, we register them. So all the brains will be aligned. Then we get rid of the skull, the bones, and we stay only with the brain area. So the gray and white matter area. So the brain extraction. So we have now around 20,000 of these brains, these volumes, and there's like gigs and gigabytes of data. And we investigate possible detectors based on deep learning and volumetric input. So the input to our algorithms are the 3D images. And then when we started, we trained our solutions, and then everything was overfitting everywhere. So we went back to the planning and asked, okay, we don't have enough data to train such a complex detector because we only have 20,000 MRIs, but we have millions of parameters. So what can we do? So we went back and we discussed several approaches, like better regularization, changes in the layers of the networks, higher dropout rates, working with sizes, adopting multi-class hinge losses, and doing lots and lots of data augmentation. And in the end, we are able to achieve an impressive result if you use only the image. I experienced a seasoned specialist, a neuroscientist, or a neurologist normally will get around 80% correct, 80. But this neurologist normally uses information from the previous history of the patient and the family. We, using only the image, we activate 76% accuracy for a problem with 3 classes. If the person is cognitively normal, if the person has mild symptoms of dementia / Alzheimer's, or if the person already has strong evidence of Alzheimer's. So a 3-class problem, 76% accuracy. So now we want to explore new approaches. I just got a PhD student to explore this. She will explore the incorporation of clinical conditions, phenotypical factors, everything in the solution, and put the human also in the loop, as we have now, to improve the detection rate to see if we can go over 80%, above 80%. One other important thing here is that we not only detect what's going on, we are also interested in explaining why the algorithm took a decision. So if you look at the top left, you're going to see some red areas. So those red areas are the ones associated with a normal person. So if you can see that those areas are pretty much random. They don't have a standard. But the ones on the bottom right, they are associated with specific places, showing that the brain is decreasing, the brain is shrinking in size, and some organelles in the brain are also changing shape. Like if you look at the fourth brain on the top, the one labeled X equal 1, you can see 3 areas marked in red. Those 3 areas are changing shape. So it shows that the brain is changing due to Alzheimer. So this was, everything here was calculated with explainable artificial intelligence. So continue here, another exploration that we have in our lab goes in an attempt to protect children when they watch content online. We call this project sensitive media. And the idea here is to detect pornography and child pornography and violence and block the content so that a child cannot see it. Of course, it has a lot of complications because sometimes we have cultural aspects associated. And if we see an indigenous woman, for instance, doing a dance, we should not just block that video. And this is in terms of algorithms. Or if we have someone given a first service in an emergency, like a heart massage to resuscitate the person, this is not violence. This is like a procedure to save a life. But the algorithm typically detects that kind of thing. So how can we use technology to detect pornography and child pornography and violence? This was a work in partnership with Samsung, Brazilian Federal Police. We trained our solutions on hundreds and hundreds of video hours, and these videos were annotated frame by frame so that we could see if there was a violent scene there or if it was like a child pornography scene or something. We don't have access to the child pornography images. These images are annotated at the Brazilian Federal Police, but then we ship them the algorithms, they run the algorithms there, they are trained, they give us the feedback, and then we change the algorithms and so on. We keep interacting with them. So our solution has basically 3 stages. We start with the video in the low level, we describe this video in low level, then we calculate some median level information, and then we go to the high level where we have classification. For that, we developed like a motion detector. So here you can see our motion detector in operation. So whenever we have something moving, the detector is working. So you can see that we draw some glowing circles on top of them to show that we detected the motion. So we do that also for the videos. And then when we detect the motion in the video, we create a cube around that part that's moving. And that cube is the input to our algorithms. So we work with sequential frames, optical flow. We calculate the differences of sequent frames. And we also work with what we call motion vectors. We know the kind of motion that happens from one part of the video to another. Everything is given as input to our solution. For instance, it can be a CNN, a convolutional neural network, but it can also be not based on deep learning. We have both kinds of solutions because sometimes we need speed, sometimes we need to run this on the cell phone directly or on a smart TV. In the end, we combine the different answers and we have the decision. We are able to detect pornography with 95% success, child pornography right now 85%, and violence 80%. So this is a very good result, especially in terms of pornography. And we are still improving the child pornography and the violence, but they are already useful for the Brazilian Federal Police. The solutions with Samsung, they are being available on smart TVs, IoT devices, mobile phones, and the ones for child pornography detection is available for free. We develop a virtual machine that we ship for free for anyone interested. Many police departments are using it. And it was presented 2 or 3 years ago in the International Conference of Interpol in Singapore. And this guy on the right here is Paulo. He's from the Federal Police, and he is our collaborator in this project. Very good. Now to close, some other investigations that we have in our group in terms of forensics. For instance, we want to detect if an image like this is real or fake. We also want to detect something like this video in which like a bomb explodes. We want to be able to detect which persons were present and perhaps, we don't know, identify possible suspects. Like this. I'll analyze all the persons present in the different videos and images and try to come up with the most common faces found. So this is a project in collaboration with many universities. This is called Deja Vu because we want to see again. And I've been working in the area of digital forensics and machine learning also for more than 15 years. So some of the problems that we work here, authorship analysis, we want to analyze who wrote a social media post just based on the content. So if you go online to Twitter and you see a tweet, if we look only at the tweet content, can we detect the author based on the style of the writing? We want to develop some techniques to detect fake news, to detect forged fake components, fake photos, fake videos. We call these digital manipulations. As I showed you, we want to work with sensitive media, detect pornography, child pornography, and violence. And we also want to sort images in time to know which happens first, what happened first. If we have like two pictures of the same explosion, which one came first? Only looking at the content. So this is the kind of thing that we explore here. So let me give you an example of the fake news. So in the fake news, we work with the news piece, the comments that people put online about that news piece, and the posts in social media about that news piece. And all of these go as input to our solution, which is a multi-head neural network, and we process if there is a chance of that news piece being fake or altered somehow. About the sorting of images in time, the question that we do is, how do we perceive time? For instance, time can be analyzed in terms of dynamic motion elements. The ball will do this parable, not the contrary. Or illumination and shadow. The day goes by and then comes night and then comes day and so on. Or the season and weather factors, they change. We go from winter to autumn and then to spring and summer and so on and so forth. So after the spring, we have the summer. After the summer, we have the autumn. And after the autumn, we have the winter. So can we detect that automatically based on images? Or we have human factors. After some time, the construction changes and the environment changes. So can we see that happening? Or other human factors like fashion. People have different ways of showing themselves over the years, or in terms of the style of cars and other objects. So what we do here, we define what we call temporal anchors. We have an image as a reference, and for that image, we know the date it was collected. And then we have two unknown images, and we ask for each one of them if they came before or after that anchor that we have. So we devise all of these representations to decide where to put in time a particular image. And we did some analysis for that. One of them was for the Notre Dame Cathedral fire in 2019. And based on that, we can sort in times the different images that we collected from the internet, and to also put those images in terms of the reference in space to the Notre Dame Cathedral, where they are, if they are on the north side or on the south part. And we also detect not only what's happening, but we detect what the algorithm used to take a decision. For instance, when the algorithm says there is a spire on fire, the algorithm is really using the spire to take the decision. When you look here on the top left, you can see that the red area is exactly the fire on the spire. Or when the spire collapses, you can see that the algorithm exactly found the spire collapsing. So this is what we look for. We want to detect the events and also explain how the algorithm took a decision. Finally, what do we want? If we see an image like this, is it real or fake? So we want to design AI techniques to point to us that, well, this is a composition, but not only a composition of just two images. It's many more than that. So can we detect this kind of things? So this is something that we are interested as well. To conclude, what challenges us? The main challenges is that we want to develop techniques that are capable of learning over time. They are flexible according to the original definition, the most recent definition of AI. We want to be able to adapt to dynamic conditions. We want algorithms to be explainable. We want to detect the different biases, the prejudices that the algorithms might have. And we want to overcome these biases. We want to be able to work with heterogeneous sensors. We want to work with time series, audio, videos, volumes, text, no problem. We want to be able to work with them. We want to work with big data and small data. Sometimes in medical problems, we don't have big data. Sometimes we have problems in the sensors, so we have instability. We need to be able to work with that. Sometimes we have missing variables. We don't know the quality of the data. So we want to be robust to that kind of thing. And where we want to go? We want to go to the development of algorithms that detect and fight biases. We don't want biased algorithms. We want algorithms to be able to deal with the unknown, to be robust to this kind of unknown. Algorithms to be explainable and algorithms that are fair. Why? Because we want to act in anticipation. We want to, for instance, in the Alzheimer's case, we want to give people the chance to detect something way before so that they can improve their quality of lives. We want to open the Pandora's box. So we want to understand what's going on. It's not just developing the algorithm. We want fair algorithms. We want ethical algorithms. We want algorithms that are auditable and that are intelligible. So this is what I wanted to discuss with you. I hope that you could have a glimpse of what we do here. As I said, I'm the coordinator of the Artificial Intelligence Lab here, Recod.ai, as you can see in my t-shirt. If you are interested in getting to know us, just go to Google, just go to the browser and type Recod.ai, and you're going to see our lab page. If you want to know a little bit about the Institute of Computing, just type Institute of Computing, University of Campinas, and you're going to see. And please also follow me on LinkedIn so that you can get to know some of the research that we do here. So I will stop sharing now so that you can ask questions, and then we can have a more lively discussion, okay?
Well, thank you so much. This is not a glimpse. This is a panoramic view of everything. So, but it is completely, I don't know, it's amazing. So, I don't know, ¿alguien tiene alguna pregunta, comentario, questions, comments? En el chat.
Julieta is asking, can I go ahead and answer Julieta?
Yeah, please. Sure.
Okay. So, Julieta, you are asking if CNNs, convolutional neural networks, are used for the detection of Alzheimer's? Yes. In our work right now, we are developing 3D CNNs, 3D convolutional neural networks that receive as input the entire brain. And then when it receives the entire brain, we try to find the patterns associated with Alzheimer and some changes associated with dementia, for instance. This is expensive in terms of computing power because we need to have a GPU that's capable of fitting the entire brain, of course. But right now, it's what we are doing. One thing that we want to change now, according to some discussions with the neuroscientists, is that instead of focusing on the entire brain, perhaps we should focus on some particular parts. So the input will keep being 3D, but not of the entire brain. It will be the 3D of some particular areas of the brain that we should pay more attention to instead of just the whole brain.
Okay, thank you. Someone else? ¿Alguien más? Preguntas? Gabriel, please.
Anderson, thank you for your comprehensive talk and impressive talk. No? I have two questions, and in fact, I have a question, but I only do two questions. First, let me to the easy questions. No? We can know everything. Yes. What does undergraduate students need to move into these fields of the artificial intelligence, or not only students, researchers like me or whatever, to work in the future to these fields?
Very good question, and indeed a $1 million question, right? This is a very difficult question. What should we do to enter artificial intelligence? Well, I'm in artificial intelligence, and I need to study every day to keep being in artificial intelligence because it's a field that changes every day, every moment, right? So if you are starting and if you are interested in AI, the first thing that I suggest to you is to learn in high level what are the capabilities of AI, how AI will change the world. So in that sense, I suggest one reading that it helps a lot people that want to start in AI. The book is The Future is Faster Than You Think by Peter Diamandis. There is a translation for Spanish, there is translation for Portuguese. In Portuguese is O futuro é mais rápido que você pensa. This book is really, really good. I think that I have it here. Let me get it. So this is the version in Portuguese. Okay. So the future is faster than you think. Why I'm recommending that book? Because this book, it talks about the Convergence Revolution. So it puts AI in contrast with all of the other areas that I mentioned here. So this is not a technical book. It will give you first an overview of what's possible. Then once you know what's possible, what I suggest you to do is to go now to the technical parts. So for the technical parts, like the best book ever is this one, Artificial Intelligence. It's like the book that I use in the discipline. It's like by Peter Norvig and Stuart Russell. It's now in the 4th edition. This is just the 4th edition that came out a few months ago. This is like the reference for AI. And I really suggest you, the person, to start from books, not from articles. Because the books, like, they are more well-worked, they have more depth, they have like professors behind them trying to teach you something, not to sell you something. And an article is about selling something. So I suggest this book, Artificial Intelligence, A Modern Approach. And after you have the grasp of this book in particular, then you can start taking courses online, for instance, if you don't have the option to do the course physically in a particular place. And I recommend like courses from Coursera, from OpenAI, and there are many good courses online. But before going to those courses, I really recommend reading these books. Okay.
Okay, thank you, Anderson. I have a second question, but in the chat.
There is another one, yeah.
Exactly. Por favor, Héctor, puedes leer la del chat y después continúo.
What about the approach to conscience? La conciencia.
Very good question, Ernesto. I already take this opportunity to invite you all to our series of Recod.ai talks. We have pretty much at least one meeting every month. And the November meeting will be about AI consciousness. So the guy that wrote the most important book in AI consciousness is the one that will give us this talk in November, is over Zoom, just like this one. So if you follow me on LinkedIn, you're going to see the link and the advertisement for that. I'm also looking forward to this discussion with this professor. He's a professor in England, and he wrote the book AI Consciousness. And I myself have some written down notes to ask him. So I think that AI consciousness is a very, very difficult topic. Let's step back a little bit. What's human consciousness? Is it well defined? How can you be sure that the other person is conscious? I'm conscious because I'm feeling right now. I know that I'm here. I know that I'm talking to you. Okay, but I know for myself, I don't know if you know that you are there. So the only way is that I'm sure that I know about myself. I'm not sure about yourself. So human consciousness is difficult. Imagine machine consciousness. So do the machines know that they are computing something? No. Right now, no. Imagine GPT-3. GPT-3 is an algorithm to generate text. Well, actually, it can generate a lot of things nowadays, but let's go with the text. So there is this Brazilian author, very good writer, called Guimarães Rosa. He's a very famous writer. And well, I also know some tests about a very famous book of in Mexico, that's Pedro Páramo, if I'm not wrong. Some people did this test as well. So they trained the algorithm to receive texts of like Guimarães Rosa or this book, Pedro Páramo, and to generate texts following that trend, following that pattern. It's terrible. It's terrible. It doesn't do that because the algorithm doesn't know what's generating. Sometimes it generates some text. It's very easy to generate text nowadays for sports news, for like stock market, because it's a standard. It's like that. Yesterday, Monterrey had a game with São Paulo, and the game was 1-1. So you just leave the blanks and the algorithm will go there and right. But now ask the algorithm, which teams played yesterday? It will know, São Paulo and Monterrey. Okay, but was São Paulo happy with the result? Probably it will not know what we are talking about. So there is no consciousness. There is no sense of being here now. And I think that we are very far away of that yet, but I'm not a specialist in AI consciousness, so I kindly invite you out to the talk in November. And the specialist, the most appropriate person to talk about this will be present, and it's going to be a fun discussion.
Thank you. Well, I have a question. It's for the students. Suppose that I want to apply to your postgraduate programs, PhD or master. What kind of background can I need? I mean, physicists, mathematicians, statisticians. What else is welcome?
right now, the Institute of Computing accepts pretty much anybody from the what we call the exact sciences. So it can be a geophysicist, it can be a statistician, math guy, physics guy, electrical engineering, electronic engineering, computer science, computer engineering. So it's basically a person that has a background in calculus and algebra and probabilities. So the three most important areas for us is if the person had a background in probability, linear algebra, and calculus.
Good.
And AI is the same thing. If you want to follow for AI, is basically these three areas.
Yeah, sure.
If you know numbers and if you know probability, you can learn everything in AI.
Yeah, and of course, programming is a very important tool to carry with the student, right?
Programming is very important, but for us, the most important is the theoretical knowledge in these areas. And we understand that if a person is still not a very good programmer, this person will have the chance to learn programming. But if the person does not know mathematics, it's very hard to learn programming, right? So that's why we put more weight on the math side. And language, there is no definition of language. The language is something that the student decides with the advisor. So some advisors will work with C++, others will work with Python. In my group, I give the students the freedom to work with the language they want as long as they solve the problems that I give them to solve. So there is no requisite in terms of language. So if you like Ruby, you can program in Ruby.
Ok. Bueno, ahí está. Estudiantes para el que quiera solicitar. Gabriel, ¿alguna otra pregunta? Comentario.
Sí. Anderson, in the same venue of the Professor Belmont questions, I have a hard questions. No? How the machine, computers, robots learn or to get learning? That means the machines, the computers, the robots have to update the knowledge with the new data. How do they do that?
How do they learn, you mean?
Yes, of course. Also. How do you get the new knowledge by the new data in the in the machine context, in the robot context, in the
It really depends on the approach that we take. So I will give you some examples, okay? So in the low level, everything is translated to numbers. So if you have some information in the word, this information will be translated. It needs to be translated to a vector. So for instance, suppose that you were analyzing an image of a face, and you want to recognize the particular person in that face. So suppose that you are in this particular scenario here. You have the cell phone and you want to unlock it. So you need to observe the word, and you're going to do that with the camera. So the camera observes the word and takes in the data. The data now is in digital form. Now this data needs to be represented in a vector form. And the algorithm will need to work on top of that vector form. So if we use what we call deep learning, the algorithm, the network, the neural network is capable of receiving this image directly, because in the end, an image is just like a vector. If you put the pixels point by point, it is like a linearized vector. So this neural network can receive this image, and the learning is basically the function that you need to learn on top of that input that will translate that input to an output. So let's give an example. Suppose that you have 10 houses in a neighborhood, and you know the area and the price for each of these houses. So your target is the price, and your information of the word is the area. So this is your training set. So what you want to learn? You want to learn a function on top of the area that will map the area of the properties to the price. Okay? So how can you do that? Well, the simplest algorithm in the world would be calculate the average of the areas and decide the price per square meter. And then this is like no learning. You just calculate the price per square meter and you have the price of a new apartment that you want to sell. For instance, you had 10 as training. Now one comes in and it says 100 square meters. What should be the price that I give this apartment? So you just get the price per square meter and you give to this new apartment. This is bad, but if you wanted to do by average, you could do that. But suppose that you want to use something based on learning. So suppose that you want to learn with an algorithm that's linear. So an algorithm that's linear, you can, okay, I have 10 examples, which means that I have 10 points in the vector space. What is the simplest form of connecting 10 points in the vector space? A line. So I can do what we call a linear regression. I will find the line that goes on top of these points with the minimum error, and then it will give me the price of something new. And the distance for each point to the line is the error. So if the line goes exactly on top of the 10 points, the error is 0. Of course, the line will not be perfect. It will have some distances to each of the points. The summation of this is the error. So what's learning? The learning is when you sum up the distance of each point to the network, to the line, and you want to decrease that distance. But we are talking about a line. So how do you decrease the distance of the line to the points? You change the parameters of the line. What are the parameters of the line? 2, the inclination and the intercept to the y-axis. So now you give another set of inclination and intercept, and then you calculate a new line. What's the error? Oh, it's bigger than before. Okay, not good. Give me another inclination and another intersection to the y-axis. Oh, this is good. So get rid of the old result and let's use this new parameter of the line. And you keep doing that until you find the minimum. So learning is basically a function of optimization on top of a cost function. What is the cost function in this example? The distance of a point to the line. Okay. So I want to minimize that. So this is an example of a linear regression.
Okay.
But we can do that differently. You can do that with other algorithms.
Okay. Let me complain. I would like to hear in your talk about the framework of the Bayesian learning. What Bayesian learning? Because from the Bayesian learning framework is a natural way to get new knowledge, to learn. No? And what do you think about in this case, to the relationship to the Bayesian learning and the...
Well, the Bayesian learning is another form of learning. The one that I mentioned is the cognitive learning based on networks, on geometric algorithms. It's basically optimizing for a cost function. But you have another way, which is all about modeling what you know, what you knew before, what's the new evidence that you have, and how do you update the world? How do you update your model about the world? This is basically the formulation of Jude de Pearl with Bayesian networks and all of the Bayesian knowledge. And it's a very powerful way of learning, and it's complementary to the way that I just explained it, to the way of minimizing cost functions and other things. So the Bayesian learning is a different way of learning in which you analyze what you have, calculate the likelihoods of all the events that you have, and update those events upon seeing new evidence. Okay?
Okay.
There are some approaches that try to connect both words, but mostly what I see is that some people go to this direction, Bayesian learning, and other people go to this direction, and sometimes they don't talk.
Exactly.
But it's a completely feasible and powerful way of learning. Right now, we are investigating Bayesian learning for causality. So the main reason to use Bayesian learning is to understand causality. So does A imply some change in B? With the traditional way of learning, deep learning, for instance, there is no way you can learn that. There is no way of finding causality, because all you know is a black box that processes your input and gives you an answer, but you don't know the causes. With Bayesian learning, it's different. If you are able to collect the data appropriately and find the priors and connect everything, then once you have the network, you can point out, oh, A really causes some changes in B to B. So this is one of the main reasons that we are exploring Bayesian learning in terms of understanding causes, because correlation is not causation. So with the other way of calculation, you find correlations, not causes.
Okay.
Okay.
Thank you. Thank you.
Thank you. ¿Alguien más? Someone else wanted to ask? Yes, Fernanda Santiago.
Yeah, thank you. I have a little request, Professor. So could you show again the book of artificial intelligence? I didn't write down the author.
The title and author.
The book.
Yeah, the
book, the green one.
I'm gonna write for you in the chat here.
Thank you.
The Future is Faster Than You Think by Peter Diamandis. But I'm almost sure that there is a translation to Spanish already.
Yeah, it's okay in whatever language. And the one that you showed, I think it was green one, of artificial intelligence.
Yeah, the other one is Artificial Intelligence, a Modern Approach by Peter Norvig and Peter Norvig. This one.
Yeah, thank you.
Okay.
Thank you. Okay, someone else wanted to ask something, comentar algo. ¿No? ¿No se animan? Ok, bueno, seguiremos en contacto desde luego con el profesor Anderson Rocha. We will be in contact for the future interactions, for sure. And, pues estamos muy agradecidos. Muito obrigado.
Muchas gracias.
Por la plática. Y pues les agradecemos a todos haber participado, digamos, en esta conversación con el profesor y haber sido expuestos a las ideas de inteligencia artificial. Son ideas modernas, pero casi todos estamos en una división en la UAM donde se estudian estas, digamos, ciencias, aunque sea por separado, ¿no? Yo creo que es una visión panorámica que nos deja a muchos qué pensar, ¿no? Sobre todo el futuro de nuestro propio desarrollo, ¿no? I want to thank you again, Anderson, for to accept the invitation to talk to us, to this audience. So, and we will see you in the near future. I hope so. Maybe in the presence of you, consciousness.
Com certeza.
You will be.
Muchas gracias pela invitación. Muchas gracias. Foi um prazer hablar nesta charla. Nos vemos.
Thank
Gracias.
you. You're welcome.
Gracias a todos.
Bye bye.
Hasta luego. Bye.
Gracias.
Bye.